So in this second video, I'm still focusing on probability, but this time we're looking at something a little bit more complex. So last time we were just looking at what are the odds, what are the chances of us getting a particular gamete or a particular offspring, knowing what the parents are. Now, sometimes what's going to happen is, let's say we flip a coin and 50% of the time you get heads and 50% of the time you get tails. That's perfect. That's exactly what you expect. But suppose I told you I flipped a coin and 100% of the times I got heads and 0% of the time I got tails. Then you'd probably ask the question, okay, how many times did you flip the coin? Because I flipped it once, expected. If I flipped it twice and I got tails 100% of the time, you'd probably be okay with that. If I flipped it 3 times and I got tails all 3 times, you'd probably still be okay with that. 4 times? Some of you might still put up your hand. At what point would you not be okay with that anymore? Would it be 5? Would it be 6? Would it be 7? There has to be some time where you disagree. But your different level of tolerances on the risk or the chance of it being a weighted coin or something going wrong could be different. One person might say at 4, I'm done. Another one might say at 7, I'm done. So we need some mathematical way to be very strict as to whether or not we agree or disagree. So one of the tests that we run is a probability test in genetics. It's called the ChiSquare test. It's a goodness of fit test. So it's basically determining if the data matches the expectations. Okay? So these goodness of fit tests, there's quite a few of them. If you decide to take university biology, then there's a good chance that you will see some of these courses. And these courses, you'll go over a variety of these particular tests. Okay, so I'm just trying to move my thing around here. So a goodness of fit test. That's what the ChiSquare test is. And I'm gonna model what the ChiSquare test looks like. In class, we would have used candy and we would have determined whether or not the candy had the right distribution. We would expect equal colors and everyone likes rockets. But we're not in class, so I'm just going to talk you through the process. I'm going to give you a virtual lab to kind of work through, and then you can hand it in if you'd like to see if you understand it. And then on the rebop activity, there will be a ChiSquare question. Okay? So when you are running a test, there are several things that you need to know in order to determine if the ChiSquare test is allowed to be used. 1, if your sampling is biased, meaning that you're going to pick black beetles because they're easier to see, or you're going to pick white beetles because they're tastier or something like that, you can't use the ChiSquare test. The sample cannot be biased. Also, generally speaking, we run the ChiSquare test when the sample size is very small. So when the sample size is large. So if the sample size is large, the ChiSquare test works nicely. If it's small, so typically less than 50, then small numbers, there's a lot of random errors that can really sway the data. So you have to be careful. All right. Now, when we run the ChiSquare test, it's a science process. So the first thing that we do is we develop our hypothesis. Okay. It's not here. So you develop your hypothesis. So we've talked about this before in science. You've done this in grade 9, you've done this in grade 10. So here we are. This program is not cooperative. Here we go. I'll use this here. Once you develop your hypothesis, then you're able to run the data to see if the results match your expectation. The ChiSquare is relatively straightforward. What you're going to do here is you're going to make up a table of values, and you're going to run these calculations, and at the end you're going to get this value, and you're going to compare this value to, it's called a p-value. You're going to compare this value to this table here, and if your data matches or is less than the p-value, you'll accept your hypothesis. If it's greater, we reject the hypothesis. So let's just run through an example. First of all, here's the ChiSquare. The ChiSquare has a Greek symbol, chi, it's squared, equals the sum, that's what that E stands for, sigma, and then you'll see a bracket, observed minus expected, all squared, divided by expected. So that's a lot of information. But if you follow the process, it's really easy to use. Okay? So in this, if your chi-square value ends up being less than the p-value from that table I showed you, then you can say that the hypothesis is accepted. If it's greater than, then you must reject the null hypothesis and make a new hypothesis. So the example I'm going to use is here, right? In a monohybrid cross, you would expect, let's erase all this, put this together here, erase all this. Right. In a monohybrid cross, you would expect to get a 3-to-1 ratio of tall plants to dwarf plants. So we've done this already last week. So if you expect 3/4 to be tall and 1/4 to be short, then you can tell us how many actual number of plants in a population will be tall versus short. So if a population of 88 plants, I'd expect 66, 3/4 to be tall, and 22, which is 1/4, to be dwarf. Okay? But we know that when you actually run the experiment, you might not get the same data. You expect that to happen, but that's not what you actually get. What you actually got was 75 tall and 13 dwarf. So the question is, if you have 75 tall and 13 dwarf, does that observed data, is it within the range that allows us to accept that the parents are hybrid? Okay? And that's what the chi-square test will allow us to do. So let's run through the process here. Now I might have to switch this over to the other screen if my whiteboard here doesn't work on this particular application. So expected. We expect out of a population of 88 that 66 are going to be tall and 22 are going to be dwarf. But we actually observed that 75 are tall and 13 are dwarf. Okay, so now the next part of this equation, I have to observe, take the observed minus the expected. So it's going to be 75 minus 66. So I can see my program here is not going to allow me to write on here. So I'm just going to quickly screen capture while I'm making this video, and I'll bring this over to another program. Copy, close that, come back here, get this out of the way. Make a new thing, paste, get that out of the way, get larger. All right, so I'll be able to write on this. Get even larger. So I want observed minus expected. So that's going to be 75. Whoa. So we get this any bigger. Nope. 75 minus 66. Right? And so that's going to be what? 75 minus 66 is, if I was in class, I'd expect an instant answer, but then a lot of you would look at each other because you don't, you're not sure this math, but that would be 9. And then down here, I'm going to have 13 minus 22, and that would be 9. Then this next thing over here is observed minus expected squared. So now I'm going to do 9 squared, right? That's my answer. So 9 squared is 81. And down here, observed minus expected is 81. And this final one is observed minus expected all squared, which is this column, divided by expected. So this is going to be 81 divided by 66. And this is going to be 81 divided by 22. So when you stick that number in your calculator, 81 divided by 66, you're going to get 1.22. It's actually 1.227, so let's say 1.23. And 81 divided by 22 will give you 3.681, so 3.68. And if you looked at the formula, remember it was a sum of observed minus expected squared divided by expected. So you take every single value in this column, no matter how big this column is, if it's 2 rows or 4 rows, and you add them all together. So I'm going to take 3.68 plus 1.23, and that will give me a value of 4.91. Okay, so my chi-squared equals 4.91. So I'm going to compare that value. Now there's one last determination you need to know, and that is something called the degrees of freedom. The degrees of freedom, which I'm going to call df for short, is equal to the number of choices minus 1, or number of classes minus 1. So I have a tall class and a short class, a tall class and a dwarf class. So it's 2 classes minus 1. So my degrees of freedom is 1. Now that I have this information, I'm able to return back to my chi-square table. And I go back to my chi-square table. My degrees of freedom is 1. And in genetics, for high school especially, we use this 0.05 column. You'll see that my value here is 3.641. The value I determined was 4.9. So my value of 4.9 is greater than 3.641. So let's write that out. Since chi-square of 4.91 is greater than 3.641, which is the probability on the table, therefore reject the null hypothesis. And the null hypothesis was that we had a monohybrid cross. So that's rejected now. So the parents are not, they're not this. That's wrong. We've determined, based on the chi-square value, that this is wrong. It's not a monohybrid cross. If my value here had been less than 3.641, then I could have said, okay, accept the hypothesis, we're good, we're done. Now I have to reject it, so I need a new hypothesis. Maybe it's a hybrid crossed with a homozygous recessive or something like that. That's something you have to determine, right? So that is the chi-square. So at this point, normally in the class, we practice this a bit more so that you guys could get some comfort. We'd do an activity where we're all kind of guided. I kind of guide you through the discussion and then the activity together, but we don't have that luxury. You're online. So I will give you a couple of online resources to work through. And the activity you're going to work through is a dihybrid cross corn lab. You'll notice on this particular graphic, let me just grab it here, see if it will let me paste it in here somewhere. Okay, big. In this particular graphic, it is a dihybrid crossed corn. This corn has 2 traits. One is for the color, and the other one is for starchiness versus sugar. The activity you're working on is the corn genetics lab. And when you look at this corn, so you're used to seeing yellow corn, you eat it, it's sweet, you're good to go. But there's many different types of corn, and we can breed it for certain types of phenotypes. So we can breed it for color, so it can be purple or yellow. And we could breed it for starchiness, so it can be starchy or sweet. And if you look at the corn, you'll see that when it's starchy, it's puffed up. And when it's sweet, it's wrinkled. So what you're going to do is you're going to get a piece of corn. I'm going to take some pictures tomorrow at school, so I'll just upload them to the Google, to the D2L environment. And so I'll take some pictures and you can count a couple of corn. You'll only be able to do one side, but that's okay. Normally we count the entire corn all the way around, and that's pretty tedious. So this will go by pretty quickly. So you're going to count 2 different corns, and you're going to count how many purple starchy, how many purple sweet, how many yellow starchy, how many yellow sweet. Okay, you're going to do that for A, and you're going to do that for B. You're going to total it up. And you want to have 2 corns so there's less counting error. The more sampling, the larger a sampling size, the less likely you're going to have like little tiny errors. Okay, and then based on that information, you're going to try to tell us which is the dominant traits. Is it the purple or the yellow? Is it the starchy or is it the sweet? And then you're going to run it through the chi-square analysis. Since it's a dihybrid cross, we have a certain ratio that we expect, 9 to 3 to 3 to 1. Cohort A, you've done the 2-trait problem. Cohort B, we haven't done the 2-trait problem. So this gets a little bit more difficult for you. So I'm telling you what the ratio is. It's 9 to 3 to 3 to 1. 9/16 over 3/16 over 3/16 over 1/16. That's what we expect. But when you count the corn, you'll probably get something else. So then, using this information, you're going to try to run through the chi-square analysis. So what I'll do is I will upload a document that will run you through a corn simulation so you can see how it's done, and then you can try to model that and do it on yourself. And then if you have any problems, you can run it by me and then we can talk about it. On the Rebop, it'll have a chi-square analysis that you can try as well. Okay, so there'll be a Dropbox where you can put the corn genetics lab. I'll take a look at it. Again, this is completely optional. You don't have to do this. You can skip over it if you're not happy with the math, if you're uncomfortable with the statistical analysis, then just leave it as a gap in your learning. All right. That's it. So good luck, and I'll see you guys on Wednesday.